is number 9. Dimensions 7. Weight 80 kilograms. Shape open-sided, which is a number 3. I need to verify my list. Holding ability 20 objects, roughly. Fragility, low, which scores a 5. Supporting ability, high, which also scores a 5. In total, the number for this object totals to 120, which is the highest scoring object out of the 10 objects I've selected so far. So it's number 9 comes first. Next comes object number 3. It has a size of 6, has a weight of 60 kilograms. It has a structure of 5, which means that it's a square structure. It has no holding ability. And it's not fragile at all and able to support other objects. In total, this is scoring 181. Next object. Would be number 2 at 27.6. Object number 2 is 1.6 meters, which is the number of all of the different lengths of the object added up in total. It's scoring number 1, 15 on weight, 15 kilograms. It's scoring number 4, which means that it has it's thin but also square at the same time. It has no holding ability. It has medium fragility and very low supporting ability, which scores it that 27.6 score. Next would be object number 1. Has only 0.15 centimeters. It has a weight of 0.5, which is 50 grams, or maybe 500 grams. 500. It has a strong structure no holding ability, but it's not fragile at all, and it has high supporting ability, which gives it its score of 16.65. The next object is object number 4. It has 0.2 meters in total. It has 500 grams of weight. It is a square object. Has no holding ability, but it's strong and can support other objects on top, giving it a score of 15.57. Next object. Let me just tick these off first. Number 5, which has 0.9 90 centimeters in total. It weighs 1.5 kilograms. It is square, has no holding ability, and again is strong and can support other objects, giving it a score of 13.4. Next is object number 7. It has 20 centimeters in total. It weighs 400 grams. It is a thin object with no holding ability, partly fragile, and also has some availability of holding something above it, which gives it a score of 12.6. Next object is 9, is object number 10. It has 2.1 meters in total length, width and height. It weighs 2 kilograms. It has no relatable shape, which means it's a fluid material. It has no holding ability. It is not fragile, but does have limited supporting ability, which gives it a score of 12.1. Next object is now object number 8. which has 0.31 meters of size. It weighs 400 grams. It is a thin object, likely a painting. It has no ability to hold other objects. It has somewhat level of fragility. And has no ability to support other objects, giving it a score of 8.56. The last object is object number... Oh, made a mistake. No, I didn't. It gives it a score of 9.71. Sorry. The last object is number... that's it, I think. Yeah, last object is number 6, which has 0.16 meters in total. It weighs 400 grams. It has a thin shape. Has no supporting ability. Can't hold many objects. And it gives it a score of 8.56. In total, we have all these scores now. So you can discard this list. Move on to figuring out an appropriate method of arranging the objects in the most efficient way possible. You can see here I've sketched out a large square, and so our aim is to solve this puzzle by inventing some type of algorithm which, as to the best of my ability, will divide and sort up these objects. I think before we begin to think about that, I need to kind of assess kind of what qualities can we attain from the function of certain objects which can be used to our benefit in more efficiently combining together certain things. So for instance, it might be the case that certain paintings or canvases are functioning in a more efficient way if they're stacked directly next to each other rather than just simply filling out vacant spaces. And there should be a value of natural attraction that is attained towards certain objects that are easily stackable. So essentially, I think the first thing is to figure out how can we assess whether a given position within the square is appropriate enough to hold that object in its most ideal position. Well, it first starts with understanding that clearly the first observation is that the largest object, object number 9, which from my memory of recording it is a large sofa. So that's why it has holding ability, because it feels partially a rectangular box but at the same time has this large cavity, and that functionality can be used as a benefit to place objects within that cavity, so that when the object is stacked into this larger area, it's going to work with the thing. So firstly, we'll have to find a position to place this in. So we could firstly place it vertically, but then that disables our ability to place objects within it unless there is something that is kind of supporting it from another angle, facing and butting up towards the side. So ideally, from my initial idea, is that it should be placed as it would be normally within the 11.5 meter grid. One thing we can at least do is, from my research of bin packing algorithms, most of them operate using a coordinate system in which the space is divided into equal amounts. 11.5, how many should we do? 1, 2, 3, 4, 5, 6, 7, 8. 11.5 divided by 8. Not necessarily to me figuring it out. I'm gonna run it this way. It's always a lot easier because I'm running with the grain of the wood. What's the time? 11:05. I will be announcing the time every now and then so that I can align the two cameras same way a clapperboard would do. 1, 2, 3, 4, 5, 6, 7, 8, 9. Seems that we've got 9 squares in this direction and 8 squares in that, but I mean, it doesn't necessarily matter. Well, clearly one area that can be proven true objectively is that the sofa must be placed along the edge of the grid, and with its back, it's straight back facing towards the area. So let's do this. Let's draw a smaller version here. The sofa will be placed in this position. With its back facing towards the edge, meaning that there's no wasted space. And then within that, there's 2 areas that we can divide the sofa up. The sofa can be divided in the vacant area that sits underneath its legs, and equally, and perhaps more significantly, the area that sits between the 2 arms of the sofa. Each of these probably have a volume which can hold most definitively objects one, because that's 0.15. It can hold object 4, because none of these lengths, even when combined in total, exceed the perimeters required to fit within here, because this in itself is a number 7. And object number 7 also can fit within this. So 1, 4 and 7 are now placed within this area. This is interesting. Now I'm thinking, well, we've got all these numbers, they're essentially telling us where to put these objects. I mean, the heavier objects, they go at the bottom, and the lighter objects go at the top. So let's do an order of different qualities, each different area. So we'll do one for size, we'll do one for weight, we'll do one for structure, and then these values of order will then negate each other to average out, and then they will neutralize and average out, and I'm proposing that this average then is a numerical description of the object's placement within the box, and then we can actually ascribe values of weight and size to the grid space, which can then use that to pair up a given number to that, and it's a function of a valley in which we have 4 different dimensions we're working in, for instance, and what I'm trying to demonstrate is that, like rolling a ball into like a valley or something, it will innately either settle in one direction, settle in the other. So it's either going to go in one particular direction. So structure, I'm just writing structure for now. Just need to verify the cameras are still rolling. Can that be seen? Yes, it can be seen. HOL, which stands for holding ability. Size, weight, structure, holding ability, fragility, FRA, we'll write for that because we're running out of space. And then stackability. Okay, is that all the values? I'm probably missing one. Let me just make sure I haven't missed any. No, I haven't. Okay, so size. For value of size. For size we can have, obviously 9 is the first object. Alright, 7. Next object. Number 3. That's 6. Next object is number 10 at 2.1. These are all in kilograms if you've forgotten. Next object, number 2 at 1.61. Next object, number 5 at 0.91. Next object, I think it's 8 at 0.31. Next object would be there's a tie between 4 and 7. Well, if we look at weights, then let's put 4 high, because that seems to have a slightly higher weight. So 4 at 0.2, and then 7 at 0.2 obviously as well, and then it's either it's a tie between 1 and 6. 1 is 1.15, 1 is 1 point, and 6 is 0.16, sorry. So it's 6, 0.16, and then 5 at 0.15. I've got where's 1? Oh. It is 1. 1, 2, 3, 4. Okay, we've got all of them. Right, now for weight. So, in terms of weight, for weight, seems that obviously object 9 comes again at 80 kilograms. Object 3 at 60. It's 15. Then object 10 at 20. Oh no. No, it's either 2 or 20. It's 2. Yeah, it's 2. So, no, it doesn't, it's not object 10. It's object 2 at 15 kilograms. time is 11 11:17. Two at 15. Then 10 at 2. Then 5 at 1.5. Then there's a tie between 1, 4, and then for 0.4 there's 8 and 6. 1 and 4, let's do 4, 0.5, and 1, 0.5, and then 8 at 0.4, and 6 at 0.4. So that's weight, structure. For structure, object 9 is at scoring a 3. So it's not the first. I mean, they're all 5s, aren't they? I have to put them in order of number, I think, for structure, because there's so many that are the same. It's the highest number with a 5. I'm going to start this list by drawing over it too much, which is really annoying me. That's even just as difficult to read, actually. Okay, it's 5 at 5, 4 at 5, 3 at 5, and then 1 at 5, then at 4, 8 at 4, 7 at 4, 6 at 4, 2 at 4, and then 9 at 3, and then it's just 10 at 0. Okay, let's follow that. Holding ability. The only one that's got holding ability. Does 10 have holding ability? No. Does 9 have holding ability? Yes, and it can hold 20, so 9 at 20 is the highest. 8. No, can't hold anything. 7. I know it can hold 3. So I assume 7 at 3. 6. Can't hold anything. 5. Can't hold anything. 4. Can't hold anything. 3. Can't hold anything. 2. Can't hold anything. 1. No. So that's it. Okay. And then 10 at 0. 9 at 8 at 0. 6 at 0. 5 at 0. 4. 0. 3. 0. 2. 0. 1 at 0. Okay. Fragility. 10 scores a 3 on fragility. 9 scores a 5, so 9 at 5. 8 scores a 3. 7 scores a 3. 6 scores a 3. 5 scores a 5. 4 scores a 5. 3 scores a 5. 2 scores a 3. 1 scores a 5. So 10. No, 10 does score. 10 does score 5. 10 does score 5. 8. Any 4s? Any 4s? No. 8 scores a 3. 7 scores a 3. 6 scores a 3. 5 scores a 5. 4 scores a 5. 3 scores a 5. 2 scores a 3. That's it, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, stacking ability. 10 scores a 3. 9 scores a 5. 8 scores a 1. 7 scores a 3. 6 scores a 3. No, scores a 1. 5 scores as a 5. 4 scores a 5. 3 scores a 5. 2 scores a 1. 1 scores a 5. 10 scores a 3. 8 scores a 1. 7 scores a 3. 6 scores a 1. 5 squares of 5, 4 squares of 5, 3, 2, 2 squares of 1, okay. 10, 9, 8 squares of 1, 6 squares of 1, and 2 squares of 1. So now we have all of the different variables organised by the structure and the size and the weight. So now we're looking to find kind of average between these, I suppose. But one thing I was thinking of while I was doing this process was that perhaps we can consider that each dimension is a different variable. Now some of these variables can be grouped together so that we can probably make 3 main categories out of these. The larger the size, the larger the weight, the lower down it needs to be. So the size and weight factors could somewhat be considered the same thing. Although we can think of size as size and weight. So so if we put for the height S and W, this axis for more unstable objects, structure, and holding ability can be grouped together. Fragility also grouped into directly correlates to height, obviously. Height, it needs to be either contained within a larger object which it doesn't touch, or it needs to be available to be placed at the top. So fragility can be grouped there. Stackability in this axis. So we can consider in this direction, moving over in this direction, the grid becomes more unstackable, more unstable. Now what that does is it allows the objects that don't fit together particularly well to discoordinate to a greater extent, and the idea behind that is that then smaller objects can then be placed within those discoordinated places. It's for me it's difficult imagining these as objects that don't have anything innately to them. I mean, the square ones, objects from 8 right through to 6 can all be, right through to 1 can all be stacked in a certain way. The structure and the size, those directly correlate. They all have a kind of bounding box to them. quite a challenge. How can I think of it? Algorithm. Branching. Try the branching method. Write some rules. Write some rules down that dictate a process of analysing the qualities of each object. Let me do some drawings. I'm thinking that of a kind of hill in which, if it exceeds a certain value, it will roll down a particular side of it, and then it will roll down another branch and then another branch, and becoming further more specialised in its position, so that the more value that it's examining, then instantaneously the more its ideal position is defined within the square. Essentially, we need to calculate the value, the volume of each object. could define everything by inputting it into a randomness calculator in which a static number is drawn depending on directly correlating to the size of an object and directly in relation to that a random number is drawn. First rule. A calculation, a random number, is generated. A random number is generated. Then you look at the size or the weight of the object. If it's more than the random number, so more if it's more than the random number, it goes down this path. And likewise, if it's less than a random number, it goes down this path. It goes down this path. What happens then after that? There's these different checkpoints. So this is size, this is weight, this is structure, holdability, and then as such, fragility and supporting ability. And eventually we have an extremely highly defined position extremely highly defined position. So now we know how we can get a machine to randomly address various possibilities. Now we need to know what separates these two things. Because it's all very well saying, well, this is more than the random number, or this is less than the random number, but we're still entering through the same questions, the same branches, okay? And this is the issue, is that there's a definition to that needs to change with each consecutive branch. So this branch could be a branch for height. So this size, if it's less than the random number by a certain amount, it goes on this height. If it's more than the random, and then this way, if it's more than the random number, it goes on this side. And you know, so and so and such and such. But then when if we are to put the object through this function, what emerges from that, in a sense? I think the important thing to recognise here is that I no longer have reference to the original, what the original objects are anymore. I don't need to know what they are. It is an exercise in purely understanding the relationship between values and trying to communicate that in this art exercise. So what am I trying to do? Because I can't find the most efficient stacking. I can't define I could define a bounding box within each object. So each object has a bounding box. Each object has a bounding box, and and for the objects that have less structure to them, okay, there's a uncertainty that goes on around this bounding box. So there needs to be cautiousness and uncertainty. But as long as the perimeters of the bounding box are still intact by the smallest, largest height, it doesn't matter whether the object had 1,000 spikes coming out of it. The point is that the bounding box is defined, and then depending on the quality, which is where structure can then be introduced, is then depending on the quality of the object, the structure, we can add in another value called uncertainty, and the value of uncertainty can be something that how can that physically emerge? Value of uncertainty increases. Okay, so we have this idea of uncertainty, which is, as I've talked about in my reflection, it's open to possibility. Uncertainty equals possibility, which increases the number of branches. Okay. So by increasing the number of branches, we are increasing the efficiency equals possibility. I think that all branches have to be explored at once, and there needs to be a collection of volume. So we've got this object here, this object here, this object here, and then an object here. We need to calculate, have a relationship. So we're exploring all this possibility, we're exploring all this stuff. And we need to we establish a predefined position in which the object eventually ends up in. So let's say this is where the object ends up on this branch here or something. What are we changing with the eventual outcome? What is being re-established? What is the variable that is being altered or introduced each time? Size, as we've spoken about, increases can be considered a function of well, it's not a function of height. It's weight is a function of height. Size is simply we're looking for the most available volume after each time the function is running. Each time the function is run, the most available volume. Each time the most available volume. That remains. So each time the function is run, the most available volume that remains. Which is what we want. We want the highest number of objects with the least number of volume. So what is this arrow representing? Well, it's not. This is the attempt. This is the attempt. This is the attempt. But the attempt is only futile until we receive a score of efficiency, which is a reaction to the attempt. So for instance, we put the object in a random position, that's our attempt. We did that on the basis of logic that we can, to the best of our ability, reinforce. But it's only until the attempt is proven accurate or achieved by looking at the amount of volume that's still remaining compared to the number of objects that are contained within that overall volume, So it's the remainder of volume that exists within the space. That's the idea. Remainder of volume. I actually want to go back to this now. The bounding box and the value of uncertainty. What has changed is that with the increase of uncertainty, the object is placed at a more placed more higher up. But then, so the rule is as value of uncertain height is naturally introduced. So the object is put at the highest possible position. That just means that it should be at the very last of the list of objects which is placed within the box. The second rule is if there is a remainder of space left between objects, then any objects with the least value of uncertainty which is remaining from the sorting is then placed in that area. Okay, so anything that can be placed within the area that there isn't an object on top of it. A cavity, if you think of it that way. So like the sofa, for instance, placed on its side or something, and we have object number 10, which has no predefined. It's completely fluid object, likely a tapestry or some sort of piece that I recorded at Chelsea. So then you're placing it in the sofa, as long as the sofa isn't kind of putting any weight or force onto it. So naturally it's a case of placing the objects. The square of the object, thinking about squareness, naturally the most square object should be at the bottom. And they should be placed flat. And they should be placed so that if there are any thin ones, they automatically, thinner ones than that one are stacked directly next to each other to keep the height at the most stable volume possible. Or you stack them vertically. Surely then the same process applies. there any case in which a position is not rule if I'm thinking now about thin objects, and I'm thinking about how you take, for instance, the idea of the rule. You think of a rule saying all thin objects are to be placed vertically to save the most amount of space possible. Now that's all well done, but what's really important is that the thin objects are if they're smaller than a certain size, they're put at the back of the list, and then once the entire all largest objects are placed first, then yeah. Why does this need to be more than a random number? I think it's time to start writing out some rules. First rule. Objects are to have the size, weight and structure averaged out. Yeah. I'm just thinking of potential problems in that case. Or is this something that is 100% objectively true? That by doing this, you naturally arrive in a position where they are naturally being organised. Then what happens? The value from that is then seven plus eight plus five and divide that by three. No? So all the numbers in the supplement. Okay. So, for instance, object number 9, 7 plus 80 plus 5 divided by 3. 30.666 recurring. Just averaging out. That's right, 7.3. Oh. I've just made a grave mistake. Just thought these were all the same. Oh dear. Let's have a go again. Let's have a go again. So, obviously 9 is correct, but not at 9. So, 7 plus 10. Fuck's sake. One, 6. Six point eight seven. Okay. 5. 0.91 plus 1.5 plus 5. 2.47. Okay. 8. Okay. 4. 0.2 plus 0.5 plus 5 divided by 3, 1.9. 7, 0.2 Don't write it down for fuck's sake. 0.2. Plus 0.4 plus 4 6 0.16 plus 0.52 5 0.15 plus 0.4 plus 1.5 plus there's 0.5 plus 1.83. Okay. So obviously number 9 first. Then number 3 second. Then number 2 third. Then number 5 fourth. And number 1 fifth. Oh no, number 5 and then this is 6. No, 7. 8, 7. 10. So now we have established the average of all these numbers. And this is the order in which they should be stacked in. So I think in terms of in terms of so 9 2 by 2 by 3 9 this is the 3 this is the 2 2 and then number 3 5 1.5 by 1.5 by 3. This could sit on top. Oh no, hold on, that's the same. That's the same length. It's just short. It's half of this, but it can't because that's unstable. Okay. But if it's 3 centimeters, overall this piece should be placed right here. I'm going to place it here. So the sofa is going here. Bottom. Right here. Put 9 here. Facing towards 9. Included in 9 is 1, 4 and 7. 3 sits opposite. 10. I've come to a realisation. The entire system of constructing these objects together can be done in the most efficient possible way by creating a system that focuses on one particular part of the box, the 11.5 perimeter area, and essentially expands the limits of it to... That's actually a bad way to explain it. Let me just write down them as rules. So the first rule is that the objects are to have their size, weight and structure averaged out, which we've already done. The second rule is then to make a list that organises that resulting number. So the first rule was to average all of things out, which we've done. The second rule is then to make a list ordering them all from lowest to highest. We've done that as well. So now, when we're working with object number 9, which is the first one on the list, what we're trying to do essentially is, since it's not a perfect square, excuse me, I'm just trying to adjust the ISO. Since it's not a perfect square, we have to essentially establish a bounding box that defines the space including the object number 9 as a square. So I can show you here. We have object 9 already here in the corner. We can see it's 3 meters long, 2 meters wide. We essentially create a bounding box which includes this angle, 3 meter length, obviously the 2 meter length, but then we extend this invisible box outwards by another meter essentially. That creates a perfect box. That box is also 3 meters high. Now, what we go from there is we attempt to calculate the remaining volume inside the box, like we talked about how there needs to be a coordination of remainder of the volume that is not occupied. Considering that object 9 is an irregularly shaped object, we then need to make an attempt to fill that box with the remaining volume until it's a complete perfect square again. Essentially what we're doing is we're establishing that 11.5 meter by 11.5 meter square, but on a miniature scale within itself. Now, we essentially, when we're creating this miniature square, we look at all objects that can fit within this, we'll call it square number 9 because it's referring to the object, and we list out all the objects from our main list, our larger list, that can fit within it. And once that has been narrowed down and we have the list of objects that fit within it, repeat the same process. We find the largest of those objects that fit within box number 9, and we essentially gradually fill it up until it creates a perfect square that's even and flat on top. And then once that and only that is done, we then can go back to our original list of the larger objects and move on to the next one, which is object number 3. So we keep building squares up of objects, trying to perfect their shape, make them perfect versions of themselves, until we essentially entirely fill the volume of everything. And all the delicate objects should, by nature, be last because of our average number that we call next at the beginning of the list. But there are a few problems and a few additional rules that need to be added as well. So, third rule. Place first object down, if a given object does not fill a perfect square of itself, an imaginary bounding box on the largest length. Okay, so fourth rule, if a given object does not fill a perfect square of itself, an imaginary bounding box of the largest length must be established and then filled following a miniaturized technique of the larger square in which it sits within. And then rule, always ensure one hundred of the box is filled if there is no object within the box. A new one can so the fifth rule, always ensure that 100% of the box is filled. If there is no object that will fit within the box, for instance if you've got only a really long object that remains within the box and every other object is either too large or is already in the box, then a new one may be established as long as all the new objects can then be restored back to the perfect square shape overall of the entire grid. The last rule only So the last rule is that only when there is no object left to fill the perfect square may there be some evenness in the filled volume. Naturally, I think that the priority list will encourage the most delicate objects to be placed last on the top. And since one of the original rules I set out in this project was to construct something that doesn't damage anyone's particular work or object and that nothing can be disassembled, it should naturally follow this. But overall, this is I'm 100% sure that this technique is guaranteed to work. You can see that I've partly established, proven this by saying that objects number 1, 4 and 7 can fit within 5, and then objects 3 can be placed to fill 9. And then obviously if we want to continue this process, we can just very quickly to prove it. So you can see I've done number 3, now we're on to number 10. Number 10, let's look at the measurements for number 10. Total it's 2.1. 70 by 70 by 80 centimetres. So we'll start over here. So we're going to be about like this. Object number 10. And the object is square. So it's a perfect square. Now we establish a box that is perfect to that. So that's 10. That's 80, 70, 70, so an extra 10 there, an extra 10 there to make it a perfect square. So we have a remaining volume. That can likely fill objects 5, object 5 can sit on top here. 0, 5. Object 6 can go here. 6. Object 7 is already there, object 4 is already there, object 8 can go here. Object 5 already there actually. Object 2, no. Yeah, you can't do that. Okay. So that's object 10. That's 5, and then that's 6 and 8, and then object 2 goes here. Object 3 is there. Object 8's already there. So we've done 9, we've done 3. Have we done 2? We've done 2. Oh, no, we have done 2, sorry. We've done 5. We've done 8. We've done 4. We've done 1. We've done 6. We've done 7. Just number 10 at 2.1. Oh no, we have done 10 as well. Yeah. This is the smallest possible area. So essentially, I would have to do a sketch of this actually, but this demonstrates basically the idea, and it's taken me in total about 2.5 hours. A very long-winded and complicated process, but this is the conclusion of the research into this stacking problem, and I'm satisfied with the solution, and yeah, this is the outcome, which I'll be showing at a more detailed level with an actual image of it face upwards, but yeah, this is the end.